Hello everyone. Welcome to Chemistry by Miss Nidhi Banga. Today we will be talking about reducing agents. Reducing agents, as you may know, are the ones which reduce others, and in doing so, they get oxidized themselves. Reduce others and get oxidized themselves. All right. So, in doing organic chemistry, you may have come across many reducing agents, and more often than not, it can get a little messy or confusing. So, my agenda today is to discuss all the reducing agents, all the important ones, and draw a sort of mind map so that you can remember them and correlate them and use them in conversions and other questions, other board questions. So what I've drawn here is the organic compounds going from the most reduced ones to the most oxidized ones. Alkanes, represented as RH, is the most reduced one. It has no electronegative atom, so it's quite reduced. Then we have alcohols, where carbon is bonded to is singly bonded to an electronegative atom, that is oxygen. So that is why it is more oxidized than alkanes. Then we have aldehydes, represented as R, C double bond O, H. Here, as you can see, carbon is doubly bonded to oxygen. You can think of this as carbon bonded to oxygen by two single bonds, so making it more oxidized than alcohols. Similarly, ketone is at the same level, where carbon is doubly bonded to an electronegative atom, that is oxygen. Next up, we have carboxylic acids, where carbon has one double bond with oxygen and it also has a single bond with oxygen, making it most oxidized of all of them. Right? So since we are doing reducing agents, our agenda is to go from oxidized ones to reduced ones. These are the ones which we find very often in our organic conversions. So let's talk about them. As you may have noticed, the first three are special reagents and their name are also sort of similar. For example, lithium aluminum hydride, sodium borohydride, DiBALH, which is basically diisobutyl aluminium hydride. So these three have hydride in them. So what is the role of hydride? How is hydride helping in reducing? So hydride, as you know, is basically H minus. Hydrogen can exist in three oxidation state: H minus, 0, which is found in elemental hydrogen, then H plus. Okay, so these are the only three oxidation states possible for hydrogen. In these three reagents or these three reducing agents, hydrogen is in the form of -1. From here, it can only go to a more positive oxidation state. So from here, it can only get oxidized, and in doing so, it will reduce others. Therefore, the reagents with hydride get oxidized themselves and therefore reduce others. That is why they are the most very commonly used reducing agents. So let's take them one by one. First one is lithium aluminum hydride, which is very strong, so strong that it can convert carboxylic acid directly to alcohols. It can carry out a two-step reduction directly. Okay. If you want to convert aldehyde or ketones to alcohols, then also you can use lithium aluminum hydride, because regardless of the number of steps, it won't go beyond alcohol. It won't reduce alcohols to alkanes. Its limit is still alcohols. Okay. Whether carboxylic acids or aldehydes or ketones, lithium aluminum hydride will reduce them till alcohol only. For this step, from going from aldehyde or ketones to alcohols, we can use another reducing agents, sodium borohydride. This is much milder than lithium aluminum hydride, much more environmentally safe, easier to handle. But this will not be able to act on carboxylic acid. Its limit is from aldehyde or ketone to alcohols. I hope you know that aldehydes upon reduction will give you primary alcohol and ketones upon reduction will give you secondary alcohols. Talking about the third one, dibial H. Dibial H is also much milder than lithium aluminum hydride. It can also reduce till some extent, not all the way to alcohols. It acts upon not carboxylic acids or aldehyde or ketone. It will act upon esters, which are also just as oxidized as carboxylic acid. Here also carbon is doubly bonded to oxygen and singly bonded to oxygen. Another compound which is also very oxidized is cyanide. Cyanides also, or nitriles, they also are very oxidized because here carbon is triply bonded to nitrogen. In both these cases, dibial H will reduce them to one step only, to one more reduced step, like till aldehyde or ketones only. Till aldehyde only. It will not reduce it further to alcohol. That can done by only lithium aluminum hydride. Only lithium aluminum hydride is able to reduce, is able to carry out two-step reduction. Sodium borohydride and dibial H will carry out one-step reduction. Sodium borohydride will convert aldehyde or ketone to alcohols. Dibial H will convert ester or cyanides to aldehyde. But dibial H has a special property, and that property is that apart from being milder than lithium aluminum hydride, it's also very selective. As in, if you have a compound where there is, let's say, a double bond, then upon treating this with dibial H, reduction takes place only in this area. Double bond is not affected at all. So your product here would be this. Double bond remains intact. Okay, so we have now done all three hydride reducing agents, right? Next up is converting aldehyde or ketones to alkanes. For that, we have name reactions. One name reaction is Clemmensen reaction, which uses zinc amalgam in presence of HCl and converts aldehydes or ketones directly to alkanes. The second one is, I'll write it here. The second one is Wolff-Kishner reduction. It will use hydrazine and then upon heating in presence of KOH and ethylene glycol, it will give you alkanes directly. Now, if you want to convert carboxylic acid to aldehydes and ketones, this step we haven't done so far because there is no single reagent which can carry out the reduction. It can be done in two ways. Either you convert carboxylic acid to alcohols by means of lithium aluminum hydride and then oxidize it, or you can also use this step. You can first convert this into acyl chlorides by using any of the chlorinating agent like PCl5 or PCl3 or SOCl2, which will give you RCOCl. This, upon reaction with hydrogen palladium in presence of barium sulfate, this reaction is called as Rosenmund reaction. It will convert acyl chloride into aldehyde. Okay. Cyanides can also be converted into aldehyde by Stephan reaction, which uses stannous chloride in presence of HCl. So, I think I've covered it all. These are the main reducing agents which can carry out these reductions. So go ahead and draw this, watch this 2-3 times, then try drawing it yourself, and I hope you will remember these and will have no problem in carrying out organic conversions using any of these reagents. Hope it helps. Thank you.